Electron affinity of 0. What species had an electron affinity of 0?
I can't think of anything specifically, but it can be like negative or positive.
It's not an arbitrary 0. That one is actually the 0 is fixed. So the 0 would be the free atom with nothing on there, and then you add an electron to that, and then you see what the relative energy is. So in a way, it's arbitrary. That is, you have the free atom with nothing, and then that point is set as 0 potential energy, but it's not really 0 energy. But since there's no electron on there, then it's just taken as the 0 point. But it's not totally arbitrary because that is something that you can measure. You measure these things, the electron affinity, and so in the gas phase, you can measure the difference in energy, how much energy is given off when it takes an electron. And so those are actual thermodynamic values. When you're comparing them, though, the 0 point's the same in all of them. And so it's not there. I mean, there is no absolute 0 potential energy. I mean, because what is it? What is the absolute 0 potential energy? What is the lowest energy when everything's been breaking apart? And then that means everything in the universe has to be broken apart and spread infinitely. And so in that sense, it's arbitrary. But in another sense, it's not totally arbitrary. Does that answer?
Yeah. Okay. And they said something about like it being exothermic or endothermic. Does that have to do with it as well, like the negative and positive value?
Yes, right. If it's exothermic, that means you're going down in energy, so it wants an electron. If it's endothermic, you're going up in energy and it doesn't want an electron. So your starting point is more stable than your endpoint for endothermic. And so if you have the free atom would prefer to just be the free atom with no extra electron. And then that's endothermic. But most atoms are exothermic, even metals. And so it's surprising because metals want to lose electrons, but it turns out that they can gain an electron and become a little bit more stabilized. Except the alkali. Alkali is okay. Alkaline earths are not okay because it goes into 2p. And then some of the others, like nitrogen, would have the pairing energy, and then the noble gases aren't good. And so those are the 3 patterns that you see for endothermic electron affinity. Okay. Were there other questions? So I don't know what progress you've made. In fact, I know some of you have made good progress on the formal report for the sulfate. Yes. So I wanted to talk about it. I wanted to show you some sample reports. Take a look at let me see if I get zoom in here. Let's take a look at this abstract here. Let me go ahead and read this. Can you guys read that? Let's see if I can focus it. Any comments on this one? All right. Okay. Well, that I guess I don't know. Even though they labeled it the introduction, maybe they forgot the abstract. That could be it. As an introduction, that might be okay. But usually the first paragraph is going to correspond to the abstract. So this is. We can read another one. This is a lot better. Uh-huh.
The previous paper was not double space. It had no indentation.
I
Was that
I like yeah, single space is fine.
single space is fine?
Yeah.
Is the indentation
Indentation doesn't matter. It could be block style or indented paragraphs. I don't care.
you want us to bold the
Yeah, usually you bold that. They're different. It depends on where the paper is going. Some people will have a very strict format, and so there isn't a set law that all the papers have to conform to this.
the first paper had parentheses for all its extra information. But in this abstract, there are no parentheses. The information is just added on. Is that important?
You don't want parentheses in abstract. Yeah. What else could they have included in this abstract? Let's see. Well, it's kind of nice because they tell us this. The individual, there were just 3 trials here. And they calculated the average, although the 6 bigs are incorrect. And what's this one, plus or minus? Yeah, the confidence interval. So they included that. We'd like to see that in abstract. So the abstract, in that sense, is good that it described what they did. There are other things they could have thrown in there in the abstract that would have made it helpful. Like what? What else do you think they could have included in the abstract to make it even more descriptive, and it wouldn't have taken much space? Well, there's one important step that would have been taken to get there. Not the filtration, because when you do gravimetric analysis is going to involve filtration. So anytime you do a precipitation reaction, we're going to be doing filtration. And so that's common knowledge. But another thing that might be taken as common knowledge, but it isn't necessarily, is what else did you have to do before this? They have the white solid. Then what do you do with the white solid? Well, weighing it, weighing is, if they showed the masses here, then they must have weighed it. So we don't need to describe the weighing, but they should have mentioned something about what? It could be, drying, the samples were dried. That would be good to add in here. Something about the dried samples. You don't have to say about desiccator, because when we dry samples, we're always careful about them reabsorbing water. And so you could say these were dried in a drying oven. That would be helpful. The drying oven, I don't know if anybody got the temperature. The temperature is 120 degrees C that it was set at. So they're dried overnight for 120 degrees C. But what else might be helpful to the reader for something like this? You could talk a little bit about the reactions, like what did you use as a precipitating agent? But before the reactions, you had to do a physical process. That physical process was what to do?
So we have to measure it out. Weigh it as well. Do we need the equipment?
No, you don't need the equipment. Any kind of equipment's fine. one thing that you want to know is, how hard were they to dissolve? And, what did you dissolve them in? Some solids you can't dissolve them easily. And so that means you have to heat them up, or you have to dissolve them in acid or base or alcohol or whatever. And so we'd like to know, these were easily dissolved in water. Or did they dissolve easily? Or those give clues as to what's going on here. The chemistry. We have choices for precipitating agents. Different choices for precipitating agents. We could have used what else? Well, what did we use for a precipitating agent? Barium chloride, right? Why didn't we use barium nitrate, or barium acetate? Well, sometimes those types of things come up. Well, let's take a look at this abstract. You tell me what you think of this abstract here. You could ignore my comment. This is a multi-paragraph abstract. Is this a good abstract? Should be short, yeah, and it should be as informative as possible. But this one has like too much information about stuff and too little information about other stuff, right? Don't you think? I mean, all right, on the next day, a vacuum apparatus is set up and 3 different solutions are poured into 3.
Step by step.
It's good for step by step, but yeah, not for the abstract. So that's another example of abstract. I see a lot of examples. I mean, I do this every semester. I see lots of people have different ideas about abstract. Well, let's take a look at this one. We'll just see some. Oh, did we? Yes. All right, let's take a look at some more so you get a better idea. Yeah, this is gets kind of to the point what they're doing. How could it be a little bit better, you think? What do you think they could have added to this to improve it?
Maybe write the balance equation.
Yeah, that's possible. They could write a chemical equation. If you write a chemical equation in abstract, then you have to write it within the abstract. You don't break it, a line break or something there, because abstracts cannot, and they have to be formatted in certain ways. A lot of journals will not allow equations to be in the abstract unless it's critical. And so you can talk about it, rather than writing an equation, you can talk about it in words. For example, if they're going to talk about precipitation, they can just tell you what the precipitating agent was. It was precipitated with, and then you don't have to show the whole balanced equation, right? But one of the things is, again, there's not enough about the unknown. What did the unknown look like here? Your unknown was a white powder. But this is okay. They didn't talk about how many trials they did. It would be good to know how many trials were done. Okay. Okay, this one's out of order here. So they put the introduction here and then the abstract. This is never done. The abstract always comes first. Right? And so there are lots of things about formatting, that depend on the journal, but one of the things is all journals will share the abstract. Some journals don't have an abstract, especially for short papers. Like if the paper is extremely short, then like 1-page paper or something, then they might not. Okay, what do you think of this abstract? Good? No, this is not good. Don't use this as a starting point here. There's so many things missing. I mean, in order to figure out what's going on here, they're going to have to read the whole paper, and that's going to piss people off to have to read the whole paper. They just want to read the abstract and be done with it. Most people, they don't want to waste a lot of time. You can see some variety here in the abstract, and then you can just figure out what you want to do. Here's another example of an abstract. This is all from just one class. Same class. Same class, but the thing during this class, I wrote the rough draft on the computer during lab. We just came up with a rough draft, but this time I decided not to do that. Just show you different examples.
It's good to use the subscripts whenever it's talking about the chemicals, with the 2 and the 4 being lower than the actual letters, right? And the exponents and the ions. Is that important?
You're talking about for the formula?
Yeah.
Yeah, very important.
To put in the subscripts.
It should be in subscript.
I noticed that other people do not use subscripts.
It should be in subscript. Most journals are going to want it in subscript, and then they have different criteria. It's got to be this many below, and it's got to be this big. And so you spend a lot of time. If you actually write a paper for publication, you spend a lot of time formatting it so it's perfect. Otherwise, it gets rejected automatically. I mean, they don't even read it. They just see the formatting is wrong, and they'll just reject it outright. Like you, they don't have time to correct every little thing. They'll just say, okay, do it over again, basically. Everybody's busy. And so, yeah, they're going to want it. Like here, the superscripts for the charge. If you didn't subscript the 4 and superscript the 2, then what is it? 4 minus 2. Or it's going to be SO4 minus 2. It's going to look weird. And so they're going to do that. The parentheses here, you don't really need them. You could have stated this. The parentheses are unusual in abstract, like this. You just state this as part of the sentence. Precipitating out insoluble barium sulfate. First was to determine the mass percentage. Dissolving the sample in the acidic, then precipitating the sulfate ions, the students were able to physically collect. You know what I don't like about this one is, when you read this, it sounds like, oh, this is something you should do. You should do this. The students should do that. but it doesn't really describe what they did. You know, an abstract, nobody wants to read what you're supposed to do. Everybody wants to read what you actually did. You know? And so this starts to read like a purpose rather than, the difference between purpose and observations. Purpose is what you're supposed to do. Observations are what you actually did. And so everybody wants to read observations, not what you're supposed to do. But the last sentence is okay here, after 3 trials. So they did 3 trials. That's good. The percent compositions were. The results have a standard deviation of 95% confidence interval. Well, they didn't really show it, but I guess this is the range, 4113 to 4121. They didn't show the average. We need to see the average, and then we can see. So is that good, or do you want to see some more abstracts?
Maybe one more.
Okay, we'll take a look. We'll take a look at some more abstract. Okay, this is always something we need, is the sample unknown number 141. Know what it looks like. We found out the portion of this unknown that it was composed of sulfate by applying gravimetric analysis techniques. Starting off, we prepared 3 separate samples containing unknown white solid, which was in powdered form. We put roughly 0.3 grams of the unknown into each of the 3 containers. Yeah. So they didn't talk about the dissolving, but they did talk about the precipitation. The dissolving is an important step, shouldn't be overlooked. To isolate the sulfate from the solution, that's one thing we should know. We added barium chloride drop flies to each container. So here they're telling us what they did, which is good. But one big thing's missing. And this is going to be the biggest thing. What is the big thing that's missing? Yeah, they've never put what they got. What was the percent sulfate in sample 141? So here they're making the reader read the whole paper in order to figure out what they did rather than just the abstract. Most readers don't have enough time to read the whole paper. They just want to read the abstract. Now, if they read the abstract and this is important to them, then they're going to read the whole paper in detail. And that's where they want to get all the details. But this is missing the most important thing. And the most important thing is, what did you get? Yeah.
For this paper's abstract, they didn't use any formulas. They just wrote it out entirely, barium chloride sulfate. Is that important? Does the writing of the formula or writing out its name?
That's a good question. It depends on certain journals. I mean, some journals they wouldn't want, or they have a preference.
So that just adds extra length to the ad.
It adds extra length. Usually they try to limit. There's a certain word limit, like this would exceed the word limit probably of an abstract. You have to write it within a certain number of words, or not words, but character spaces. And so it depends on how many character spaces you have. So you try to compress everything down.
I have one last question for this paper. The abstract and the intro are numbered with Roman numerals. Is it important to number any of these?
No.
Because none of the other ones have.
No.
And if we do need to number one,
No. No preference. No.
also should we write with the entire word introduction? Because they just wrote intro.
Intro is fine. How about this abstract?
We got the answer this time around. Where's their appendix A?
It's in the back statement. You never want to reference. You never want to force the reader to look for something in the paper from the abstract. So you never reference see table 5 or equation 6 or appendix A. You don't want to have to force them. You should contain. It should be self-contained because abstracts are just published alone. Abstracts are free. The whole paper you have to pay for. It's like $40. Unless if you need a paper, certain papers. But if you're at a university, then they pay. They have subscriptions, so you can get it all for free. And then there are people who figured out how to hack papers for free or something. But if you want to do it, it's like 36, 40. I don't know how much, but it costs a lot of money. But you can get the abstract, and hopefully the abstract is enough. They have thick. They used to have thick books of abstracts people would read. Like me, I'd read through books of abstracts. But yeah, what do you think of this? This is pretty good, would you say? Seems to be, yeah. Describes. Maybe they could say what it was dissolved in. They didn't say what it was dissolved in. Acid, base, water, hot water, cold water, room temperature water, these types of things.
They also didn't say how much was dissolved. Just
Yeah, well, they could say, they could give approximate amounts. They don't have to detail each sample, or they could, like that other abstract where they detailed the amounts. But in this place, I mean, the nice thing about a lot of this is, since gravimetric analysis is a pretty standard technique, you don't need to know about crucibles and this type of stuff. Everybody uses crucibles, beakers, and that kind of stuff. So don't worry about that. All right, so those are some examples of abstracts. Now, the introduction, you're going to see a lot more variety in. The abstracts are kind of similar. Let's take a look. Yeah. So this one, we'll just look at one more abstract. See, this one they give it, but they don't specify each individual one. But they'll give a range, which is useful to know. Are they doing this with pounds of unknown? Or are they doing it with less than a gram? All right. This one, they're giving some chemicals in here. It's fine. This one raises some questions. How was the purity tested with BaCl2? So a reader might want to know more what they're doing here. All right, so this is another example of abstracts to give you some ideas about abstracts.
in this paper, they use superscripts for things like algicide and need, which I can only assume is for the later references and appendix. But
Where?
In the introduction, algicide and need superscripts, right? Which I can only imagine is for.
This is for footnotes and endnotes.
Yeah.
And,
but the previous page did not use superscripts. It just labeled them with 1 and 2 in parentheses.
Yeah, you could do that, or you could put the author and year in parentheses. So you could use whatever reference format you want, and you could use footnotes or endnotes. It's fine. You could just use MLA. If you're used to using that, just use that. You know, there's a chapter on references that I didn't copy, but maybe I should. So, but each journal has a different formatting system for. So some journals you have to write in parentheses any kind of reference, and you have to give the author and year. And then in the endnotes, then you find the author and the years there. Most journals are like this. They'll have it as footnotes at the bottom of the page. You can just look, footnote 1, footnote 2. Well, we can take a look. All right, so let's take a look. Sulfate is, so here you just, why are you interested in sulfate? You know, or what's interesting about this method? Some people talk, well, we'll just look at some examples and you can see what some people talked about here. So sulfate ion is an abundant cation. So go ahead and read through this. So when we get to the notes here, an algicide, you know, somebody might be interested in that. And so let's take a look. So they did it as a footnote here at the bottom of the page. So we can just go here. And I guess there's a sulfate in New World Encyclopedia. Maybe a section there, I'm not sure. Normally we have more to the references, but I don't really get into some WebMD. All right, that's all right. Okay, so the first part is just kind of some general interest. The second part is talking about the experiment itself. So here we could do an equation. And when we do an equation, we'll do a line break here and then insert the equation here and then another paragraph here. Or it could just be continuation. So this is just kind of an overview of the experiment here, which is fine. Do you want to see some other introductions? Or do you guys have a pretty good idea? More introductions? All right, let's take a look at this introduction here. So this one that starts off with sulfate analysis, that's fine, that's good.
With this paper to the last paper, when they mentioned Epsom salts in this paper, they also referred to it as magnesium sulfate right afterwards. Right? But it's lowercase, and it's not in parentheses as added information. The previous paper decided to put the formula in parentheses.
Yeah,
without the name,
you know, Epsom salts, a lot of people already know what it's made out of, so it's not that important. It's for some people don't know what it's made out of, so they'll write this here. Epsom salts, magnesium sulfate is a commercial component. You know, the other one is just describing. And so it's good to write the formula. They could have put it in parentheses and MgSO4. It's fine. Yeah.
Do you put something like that? Let people know what Epsom salts is.
Yeah, in general, unless you know, you ask the the reader for this would be like a student here at El Camino. You know, not everybody knows what Epsom salt is made out of. Put it in a footnote.
Yeah, like
you don't.
with Epsom salt.
Well, Epsom salt, you don't need a footnote for that. You don't need a reference for Epsom salt because it's such a common
definition for the footnote, right? So you would put Epsom salts, then the superscript 1, and then in the footnote you would put its formula.
Okay, let's say I did plaster of Paris. Then I would probably put a footnote in there. But for Epsom salt, since Epsom salt is common household chemical, probably don't need it. Even with plaster of Paris, I debate. You know, a footnote's not really necessary there. Plaster of Paris, everybody knows plaster. Not everybody, but you know, everybody can find out what it is. You know, without too much difficulty. And so certain things like that, they don't need it. But as a treatment, then you would need it. Like this is pretty good how they had it here. Okay, copper 2 sulfate is an algicide. Okay, is that something that's really common? No, and so we want something there, maybe algicide. Or as a treatment for osteoarthritis of the knee. Something like this, we want some kind of reference so we can look. And there should be a reference supporting this here. But things like Epsom salt, no, that's not necessary. Let's see. So here, most commonly known as Epsom salt, magnesium sulfate is a commercial therapeutic substance used as bath salt. It also holds medical applications as a laxative or component. All right, here we might want something, medical component, laxative. We might want a reference there. In fact, it's probably a good idea to have a reference there. Agriculturally, magnesium sulfate is used as a substance to correct soil sulfur and magnesium deficiencies. Here we want a reference to this. But, they probably just took this from the Wikipedia. So this, I'm starting to suspect this whole thing is just taken from Wikipedia and it's reference number 1. Just don't cut and paste because that's, of course, plagiarism. We don't want to cut and paste it. But some of these are almost cut and paste because I'll just go to Wikipedia and take a look and see. In industrial application, okay, so this whole thing here is just taken from reference 1. Okay, this will be an end note, so let's take a look at the end note here and see where this came from. And so this doesn't quite correspond. Drywall and paint. Now, does that really match all that? There's a lot of information there that should have been referenced that wasn't. Drywall and paint. The method utilized for this particular experiment was gravimetric analysis, a trusted and established method for determining the mass of an analyte from the mass of a solid. A procedure developed by who many consider the modern father of chemistry, to Antoine Laurent Lavoisier, a French chemist who lived from 1743 to 1794. So we definitely want a reference for this, number 2 here. But this is kind of interesting because it talks about the history, the origins of gravimetric analysis. And so you can talk about different things for this. Okay, so it goes in talking about some sulfate, talks about the method and some of the history. And then here, we go. For this sulfate analysis, those same ideas were implemented to take the sulfate contained in 3 weighed amounts of unknown sulfate solid to form barium sulfate, which is measured and used to determine percent mass of sulfate in the final product. The procedure was repeated 3 times. The final goal was, okay, in the intro, you can talk about the experiment that you're planning here as well.
For the introduction, actually for the whole paper, do you think using proper grammar, structure, punctuation, things like that?
Yes.
So that is a very long run-on sentence. It's almost 4 full lines.
You're not going to be graded on it. Don't worry. You said, should you? Yes, you should. Am I going to deduct points for it? No, because my grammar is pretty poor. Well, so I'm just looking for the content pretty much, so I wouldn't worry too much about it. I mean, just try to.
Are we going to be graded on how close our results?
Yes, you're going to be graded on how close your results are. Your
How
percent.
much of that is going to be the grade? How much?
let's see, what was it? About 30% of your grade is on your unknown for this paper. Now, the situation is if it comes, that's 30% would be the maximum deduction. You know, most people wouldn't get that at that point, so it's typically a lot less. Most people can do okay with the gravimetric. It's not like I'm looking for pinpoint accuracy for this, although it would be nice to have it. But let's see. Okay, so do you have an idea about, you know, I read a lot of interesting, you can learn a lot of interesting things, you know, from people researching this stuff. Like, for example, in this introduction here, in 1774, German-Swedish scientist Carl Wilhelm Scheele discovered, I'm not sure how to pronounce that, baryta, which was a group of barium compounds, including barium oxide and barium sulfate. So here's a different style. You know, here's just the author. Usually we'll put the author and the year in case there are multiple Lundgrens. And then go to the endnotes and take a look here. Lundgren Anders. Oh, this is from at least the 2015 edition of Encyclopedia. I have some interesting references here. Barium sulfate was also discovered in this hot springs near the city of Taipei in Taiwan. It was found in the form of radioactive is all one word, right? Mineral composite known as hokutolite, American Journal of Science. Okay, and then barium sulfate. I've eaten this stuff before. It just tastes like paste. It doesn't have much flavor to it. Barium for CAT scan. I had a CAT scan done. Barium is a good X-ray absorber. So there's lots of stuff you can talk about. Just general interest stuff.
They give you like pure barium sulfate.
It's a suspension, so it's like a milky liquid, but it's chalky. It tastes like chalk, suspended in water. That's what it tastes like. I think they flavored it like cherry flavor, but the flavor wasn't. It just tasted like chalk.
Cherry flavors.
Then yeah, it's a big atom, barium. It has lots of electrons. Then I had another one done, but they didn't give me. I was expecting a barium sulfate cocktail again, but they gave me an iodine drink. And the iodine I had a little bit of a reaction to. Okay, let's look at the experimental section next. So that was the abstract, the intro. Experimental, usually we never do this. We never have a list. You know why? Most journals will reject this outright because it takes too much space. Look at all this wasted paper here, you know, and so they'll definitely reject this. Yeah, it's a waste of money, especially the cost of printing is huge. So they don't. Let's see here. So a lot of people like to do materials and methods and then just like to list all the materials used and then talk about the method. We don't. You have to include that in paragraph format, which is fine. So this would be experimental procedure or methods and materials or materials and methods, whatever. And so you just go through. This is kind of your observation sections from your lab notebook, basically. These are written here in a more compact form or a more expanded form. What you do. But they add, you want enough detail here that people can repeat the experiment. Some things, though, you don't need to include. Like, you'll see a lot of stuff. Let's see. Like, people will include figures. That's fine. They included figures of the vacuum apparatus. Let me see if I can find a paper that did that. There's no problem with that, even though it does take up space because of our target audience. Other people included figures. Actually, let me show you this. We could include figures, like this person included a figure of sulfate. I need to talk about this Lewis structure here. And other people included a figure of the apparatus. Let me show figure of the apparatus. The figure of the apparatus, they pretty much just took from the book.
Wait, is the Lewis structure that's on that page, is that in the introduction of the experiment?
Introduction. Yeah. Not in the experimental. Other people did this, but if you do this, you gotta tell me where you got this from. Yeah, this they probably got off Wikipedia or something. The Wikipedia one's not copyrighted, so you go ahead and use that figure. It's no problem.
Just watch until someone trademarks those pictures, molecules.
If you do get a figure, like this one's not from our lab manual here, you can't just copy it and use it without citing unless you made it yourself, but I doubt the student made it. And so this is not good. To use somebody else's work without referencing it is very bad. Don't do that. That causes a lot of trouble. The same thing here. Obviously, this is from Flynn, but you need to reference it. If you don't reference it, it's plagiarism. I mean, it's yeah, you're gonna get in trouble. Yeah, there's somebody who's gonna go, oh, they're using my figures. And so, just a simple reference is fine, just do that. Okay, I said we don't want lists like that, but tables are often done, Although this table is pretty minimal. They could have written a lot more. The table usually goes in the results section, but before we get to the results section, let's talk about the experimental section. So the experimental section, we want to be able to read through this and be able to repeat it in just the same way. So this gives all the details of it. And, here, let's see. Okay, this one's missing the results section. This went straight to the discussion. Discussion's usually it can be combined with the results. So we could have results and discussion, which is probably a pretty good way to do this particular paper, is results and discussion. And so it'd be shown like this. And this is backwards. It's always result and then discussion, not discussion then results. And so for the results and discussion section, here you could have a table. The table could just be, let me show you the table here. So this is a good table here, because this would be more results oriented, and that's what you want. Like massive sample, this is just factual. So crucible number, that's fine. Mass of the crucible plus precipitate. Note they don't say massive crucible plus barium sulfate. Because barium sulfate, that you need to convince the reader that it is actually barium sulfate that you made. But you don't need to convince the reader that it's a precipitate. You got some precipitate. It could have been heavily contaminated, or it could be fairly pure. We don't know, but it is a precipitate. And so there's no disputing that, yeah, okay, this is a mass. And the mass of dry precipitate, there's no analysis here. So these are just the results of the experiment with no analysis, just the result. So this is a good table example. This should go in the results section, not necessarily in the experimental section. It could go in the experimental section. This author put it all in the experimental section. That's okay. In the experimental section, it's just like the procedure, your cookbook procedure, but the one that you actually use. All right, so that's the results. The results are just the facts of the experiment, the results of the experiment without any analysis. In the discussion section, that's where you're going to do the analysis. So we'll combine it. We'll say results and discussion. We'll put the results there. In the discussion, we want somebody to explain why they think this precipitate is barium sulfate and what's going on with the unknown sample, and this kind of stuff. So let's take a look at this discussion section here. In this experiment, the unknown white solid containing sulfate was dissolved using water. When an ionic compound dissolves in water, the solution contains the respective ions. The dissolution of the unknown in water suggests that the unknown might be a polar molecule. Polar molecule? No, this is not a polar molecule. This would be, if it's a sulfate, it's not molecular, it is ionic. Each ion of the solid crystal is surrounded by water molecules with the negative end of the water molecules oriented. And so they're talking about dissolution of ionic solids. So that's correct. You form what we call hydration spheres. The water molecules are able to pull away the ions because the interactions between the ions is not as strong as the pull from the water molecules. So this is talking about why. The water-soluble ones, of course, will dissolve. Water-insoluble ones won't. The dissolution of the unknown in water indicates that no lead, mercury 1 is present. They miss some. What do they miss? Is present in the unknown because they are not water-soluble. The lead, well, actually silver, lead, mercury, calcium, strontium, barium. So they missed that. But,
This is experimental, right?
No,
not experimental.
this is the discussion. This is a discussion where you're going to talk about the experiment. You're going to discuss, what's going on there with the chemistry, because if you can just show the chemistry that's happening, then people might believe you. Why should they believe you? You're going to have people who don't believe anything. They don't believe anything you say. You have to explain to them and then convince it. And so you have to use arguments they're going to distrust everything you say, basically.
It's all right if you write the formula equations like that, separated by lines.
Yeah.
Barium sulfate, barium carbonate, hexachloride, barium chloride, equal that.
Yeah, normally when you write the equations here like this, some people even go further. They write a little caption saying equation 1, equation 2. That way they can, in the body of the discussion, they can say refer to equation 1 or refer to equation 2. And so they'll label each equation that way.
We get points marked off for different word form with fonts and sizes. I noticed that it's going from Times New Roman to a different font and a different size to Times New Roman again.
This paper would be rejected, of course, but would I deduct points? No. When you submit a paper, it's the referee's job to not trust anything you say. You have to prove it to them. Basically, it's like you have certain people, they'll believe everything you say. everything. Okay, I understand, or yes, but for a good referee, they're not going to believe anything, and therefore you have to explain everything in the paper and then prove it. And so one thing is, like, how do you know that was sulfate? Could it have been some other ion in the sample and then gave you some misleading results? How do you know that white precipitate was actually sulfate precipitating out and not what else would precipitate? So anyway, let's continue and see what they say. The purpose of using water was to free the sulfate ion from the salt. So it's good that it was water soluble. And these weren't present if there's sulfate present. Barium is not super selective and will precipitate with other ions such as carbonate and phosphate. To precipitate all the sulfate as the insoluble barium sulfate, while avoiding the co-precipitation of any other ions that may be present in the solution, such as carbonate and phosphate ions, hydrochloric acid was added. Hydrochloric acid was chosen to prevent precipitation of barium carbonate and barium phosphate. Are those the only two that might interfere?
No.
Was there another one?
Nitrate.
Well, think about that, because that would be the next question. Are those the only two you have to worry about, or is there something else that might fool you into thinking this? Et cetera, et cetera. And so they go through. This is good. This is good because they clearly show reactions. Although there's something wrong here. Hydrochloric acid was added. So this is good. They're talking about this, but what about this equation? Barium carbonate plus HCl. Do you see some problems with this equation? One, it's not balanced. Two, carbonic acid is not stable. What does carbonic acid decompose into? And they should have written H2O and CO2. This is going to effervesce. And so this is not good. But it's good that they're talking about it. A lot of people didn't even talk about this at all, in their paper, which isn't so good because people want to know. Now, barium precipitates out with a lot of other ions. One, like what other ions? Carbonates, phosphates, and
Nitrates.
not nitrates. Nitrates are soluble with everything. How's your solubility rules? Do you still remember those?
No.
Carbonates, phosphates, and there's one missing that should be fairly obvious. Okay, maybe we should start off with the one before that. Sulfides are all insoluble except for group 1, group 2, and then we go on to the next one. Blank, carbonates, and phosphates are all insoluble except for yeah, it's easy to forget, or maybe it's hard to learn those. It's hard to learn those, but chromates.
So that's what
Oh, did you say chromates?
I said. Yeah.
Oh, sorry, I didn't hear you. My hearing's bad. Chromate. So they didn't talk about chromate. That's obvious. Chromate would have precipitated too. Why didn't they talk about that? And how did they get rid of that? And so automatically, this paper would have been rejected by the referee. And then what happens when a paper gets rejected, they send it back to you and they tell you, fix this, fix this, fix this. Okay, then you go back to fixing those and then you resubmit it to the referee. You rewrite the paper, resubmit it, and then see what they say. And so this is how science, there's no scientific policeman. Science is self-police. And the way it's self-policed is by peer review and the peer review process. So this peer review is very important. And so this is why people hold peer-reviewed journals with a lot more weight than non-peer-reviewed. With non-peer-reviewed, you can just say anything you want, but in peer review, you have to convince like 3 referees that what you're doing is sound scientifically. Although I did read some papers that had some obvious errors that were peer reviewed, so there are some issues with the peer review process. Well, anyway, this is on here. This is driving force. So they talk about the driving force, carbonic acid. This is good. Sulfate compounds are soluble except for barium, strontium, calcium, lead, mercury, silver. Mercury and strontium and lead are toxic, so those agents were not used as so they're talking about what they're precipitating out with the sulfate with. And so this is also good because, you could use different things to precipitate. For example, why did you use barium? Why do you use strontium, calcium, silver, lead? Why barium? And so those types of things you want to discuss in the discussion section because people are curious. And then why did you use barium chloride? Why didn't you use barium nitrate? Those kinds of things pop up. And so those are things that you could address in the in here. This is actually something I told them to look at as well. Silver has borderlines. Yeah, silver is like borderline, so it's not good. Calcium cannot be in the unknown because the unknown dissolved in water. Barium chloride was chosen as a precipitating agent, but why? And why not any of these others? They talk about silver. That's all right. This is just stuff that you can make the paper a little bit more interesting, strong. Okay, then they talked about how it was slowly added. This stuff is in the experimental section, so you don't really need to repeat this unless you're talking about coagulation. You could talk about nucleation. You know what nucleation is? Nucleation is growing baby crystals, and growth is watching the baby crystals grow.
It's also the nucleation point for water into ice.
Yeah, we need nucleation site, this kind of stuff. So you could talk about that sort of stuff because what we don't want are tiny crystals, because tiny crystals, they form what are called colloidal suspensions, right? And so here they're talking about this process of digestion. And so barium sulfate forms colloidal suspension, tiny crystals that are suspended. So a lot of people talked about nucleation and growth here. You can read about it in Wikipedia or wherever. And we talk about digestion. Digestion is talked about in our lab manual. The discussion should be the meatiest part of the lab report. People want to have in-depth discussion. Yeah, you're trying to convince the person who doesn't believe anybody to believe you. That's what you're trying to do, kind of thing.
Wait, so did you say that combine the results in this?
You can combine results in discussion because we have so few results. Sometimes you have it separate, but even if you have it separate, it's usually a table, or you just discuss. Trial 1 gave this, trial 2 gave that, rather than putting that in experiment. In the experimental, you just say trial 1 gave us this, but in the discussion, in the results, you could do a subtraction. Mass of the crucible plus the precipitate, mass of the precipitate, kind of thing. Okay, and then they talk about, the sulfuric acid, the purpose of the sulfuric acid in washing, vacuum filtration. So this is a lot of the experimental kind of stuff, but here you want to talk about what are you washing? Why are you washing it? This kind of stuff. If we read this, Celis crucibles were used with 1 micron pore size. An acid wash of hydrochloric acid was used to wash. Acid was used instead of water because it would cause peptization. So this is good. You don't need a reference for peptization digestion. Those are all common. Turning the solid back into colloidal suspension. Hydrochloric contaminants of barium and chloride ions, etc. The white solid obtained is presumed to be barium sulfate. although its identity cannot be further confirmed nor its purity without further chemical analysis. Well, there are certain things, because of the washing, did they do a complete precipitation? You could make arguments for this. They shouldn't give up so easily here at convincing. I talked about this when we were discussing the lab initially. It would be nice if we had what instrument, or how could you check the purity of your barium sulfate? Did anybody recall? Melting point. Well, the problem is what's the problem with barium sulfate? What do you think about the melting point of that? Anybody think about it? Yeah, that's Tristan. That's the problem. But the other technique we could have used is what? Told you I used to do this all the time. Not conductivity. Conductivity won't identify what the salt is. Techniques like X-ray diffraction, talked about that. We have a powder X-ray diffractometer, which would have done it quite quickly. But anyway, this one, they shouldn't give up so easily because we don't have a powder X-ray diffractometer. We can't do a melting point analysis, although you should talk about that in your paper. And instead, what we're going to do is we're going to argue for the white solid is presumed to be barium sulfate. One, we're going to argue that based on what? Based on, well, somebody might say, well, why is it barium sulfate? Why not barium chromate? We're going to argue because barium chromate shouldn't have precipitated because, why? We would have eliminated that. And how did they eliminate? Barium carbonate shouldn't have precipitated because that should have been eliminated. And so assuming that we eliminated all the potential interfering species, then this should be
The only species.
right, and it should be barium, because what else could it be? You want to use chemical arguments for it. And so we're going to use chemical arguments that it is barium sulfate. It's not presumed to be. We are pretty certain it is because we took certain precautions to make sure. Does that make sense? The other thing is about the purity. We're not going to presume it's about the purity. We did actions to make sure that it was pure. What did we do? In fact, we even tested the wash to make sure that we got everything off of there. And what did we do? How did we test it? And so these types of things can be in the discussion section for that. So this was kind of weak here. It could have been stronger. It's not that we're resigned to the fate of not being able to prove it. We're just going. It's like Dalton. Dalton didn't have a scanning tunneling microscope. He couldn't manipulate single atoms with a probe, and he couldn't image single atoms with a scanning electron microscope or scanning tunneling microscope or whatever. Instead he had to argue that matter consisted of atoms based on what?
Observation.
Based on what observation?
Constant composition.
Well, in other words, Dalton didn't say, "Oh, we can't prove it. You just have to take my word for it," right? And so he had some observations, correct? And whether you believe him or not, depends your analysis. Anyway, the last part of this is doing the calculations here. And so this is good. People want to see the calculations. They want to see how you did this. So
Should we do just one example calculation or show all?
if you do all of them, will people put these in the appendix? You could do one sample calculation and then just show the other. This person decided to do all of them, which is fine. You could do all of them. This person put it in the appendix. They did all of them in the appendix. So they just attached this second sheet here. I had them, this particular semester, I had them calculate the standard deviation by hand. It's not a difficult calculation. It was useful, but for this semester, I decided I'm going to skip it. I'm going to have you calculate it by hand. So I had them calculate standard deviation by hand, and then I had them calculate the confidence interval by hand as well. And so I was looking for that. You guys just use Excel, which is a lot faster, right? But, you know, that's different. Because the report asks you not to calculate the standard deviation and the confidence interval. The report asks you to do what? Calculate the average deviation. So I don't want the average deviation. I know the report says they want the average deviation. I don't want the average deviation. The average deviation is not how scientific results are given. And so just do it the way, and this is why it's so important, I think, to go to class. A lot of people end up skipping out, but you know, the problem is you don't know what the instructor wants. You don't go to class. So here they're calculating. Here they calculate the standard deviation. Here they calculate the confidence interval, which is a pretty simple calculation as well. You can get these equations on the web. And so here. Now, a conclusion on a short paper is not necessary. We add the conclusion at the end. And the conclusion, is it a summary of what you did? No, like here. Unknown number 158 contains 57.73 plus or minus 1.95%. Conclusion, our sample of sulfate is 57.73 plus or minus 1.95%. That's a waste. We don't need a conclusion if you're just going to repeat this, right? A conclusion should tell you some additional information. And so here, in this conclusion, this is fine. You just tack this at the end of the discussion. Some shortcomings in the experiment could have been that the sample could not have been pure barium sulfate. If the sample were pure barium sulfate, then why analyze your sample, right? And so this doesn't make sense. They might have been trying to say the precipitate might not have been pure barium sulfate, but what makes them think it might not be? You know, all of a sudden they're throwing doubt into their whole analysis here. Another shortcoming that could have happened but didn't is that the vacuum could not have been working efficiently. Well, you know, another shortcoming of this experiment is the power could have gone out of the heating oven and we might not have dried the samples. You know, so shortcomings like this, people don't want to read about this. You know, they want to read something like, you know, what could have been done to improve this, you know. So if you think about this, the next time you do this, if you ever do this again, is there something that could have been done to improve it? You know, or shortcomings that aren't like that. You know, major shortcomings that would be like, you know, characterization. You know what characterization is? Characterization is your characterization of your product. So, for example, if you make a precipitate, what is that precipitate? How do you prove what that? Well, you characterize it. How do you characterize it? You measure things like melting point, its X-ray diffraction spectrum, a whole bunch of other things to prove that what you have is what you have. And so, conclusion is you talk about those types of shortcomings. You know, not these kind of shortcomings necessarily. All right, is that good? Do you have an idea what you should do? Okay.
I know what you were thinking from my paper. The media fell off right on top of my principles broke right then and there.
Yeah. Yeah, that would be,
That'd be a great shortcut.
yeah. That would be. All right, we'll take a break here and then I'm going to talk about the experimentation some more.
I'm raising the bar. I'll take a look at your paper.
Well, you're only supposed to spend like 30% of your limit to have a I usually spend it.
I spend like $10 a month.
But I have no limit, or at least my experience. And you spend less than 5 or 30%.
I don't get that.
I don't know what's also with gas and well, if I buy them.
No, I don't like
No one's registered. Literally, people are already registering for site.
Okay, my registration for something.
I don't know. Say that, but I don't know.
I'm in No problem. Oh, I'm a man. Put that on my resume.
Oh, good. Anywhere I've been at least.
What are you talking about? I'm a man. I get to get any job I want. I can walk into a store with the utmost confidence and get a job, even if I have no prior requirements. Right? I could walk up to my boss and ask for a raise. I'll get it. Right?
Not in today's world. What is it? What is it?
There's only one downside to being a man. I may be able to do that if I don't get.
I guess I didn't watch.
That's why I.
Are you kidding me? I don't see Victoria. No, Victoria. Oh, White River. White River.
I did not see one. I'm very pale. I do stay indoors. I don't get out.
I looked him up on like the college he used to work at, and he has really good reviews. This dude, okay, he does 22 ratings. He has like 5 videos, and he will only have 5. Because your hands are like skip organically.
Okay, we'll start again here. So this lab is a bit long, so we're going to shorten it. And so everybody's done what? Nitrate, nitrous acid, bromous acid here. Are we there? BF3.
I think that's you're talking about the acronym because they were doing that with us.
Yeah. I finished final report. Number 3.
All right, we're going to do 1 through 7, and then 10. I've got to write this on the board. Bicarbonate's good. Sulfur hexafluoride, 11, 12, arsenic pentafluoride, 13, phosphoryl chloride. Phosphoryl chloride is a common name. Tellurium tetrafluoride. Iodate. 13 through 18. All right, let's work on those here. All right, so just continue working on the.
So they should all have like all of it.
Yeah. Do you know resonance forms?
No. Think about them.
Okay, just draw. Have some space to draw the resonance forms. The resonance forms are just the double bond. And so you pick one of the resonance forms to do this, and that's fine. This is the resonance form, but you should draw the other two resonance forms. That is the double bond on the bottom left and the double bond at the top instead. And so you draw in the other two, and then you had to pick one to do this. Otherwise, you couldn't do it. Does that make sense? So, when we do this kind of analysis, we have to pick one resonance form out of however many it has. But that's a problem with this. Okay, thanks.
Thank you.
Did you do the ammonium and the amide already too?
No. Oh, I did ammonium, not amide.
Did I check that off?
Oh yeah, because the ammonia was the one that we did together.
Okay.
Do you still want us to do?
No.